In this video, I will show you the construction and the logical operation of NMOS NAND gate. This will be a NMOS NAND gate. That means we will construct this logic gate using N-type enhancement MOSFET only, as this will be a NAND gate. As this will be a MOS logic, therefore to specify logic 1, we will apply positive 5 volt. And to specify logic 0, we will apply 0 volt. That means the input terminals will be connected to ground terminal. Now see, as this will be a NAND gate, here we will use 2 input NMOS NAND gate. Therefore, if at least one of the inputs is at logic 0, our output will be at logic 1. And for the inputs A and B at logic 1, therefore our output will be 0 volt. This is the circuit structure of NMOS NAND gate. Here we will use total 3 N-type enhancement MOSFETs, Q1, Q2 and Q3. Okay, and the transistor Q1 will be known as loading MOSFET. Loading MOSFET. That means we will keep the transistor Q1 in on state, and during on state its channel will act like a load resistor. See, here we are connecting the gate terminal of the transistor Q1 with this 5 volt VDD source with its positive terminal. That means we are applying 5 volt at this gate terminal. So our transistor Q1 will always be in on state, and we design the transistor Q1 such that it provides an on state resistance R1 equal to 10 kilo ohm. Okay. Now look at the transistor Q2 and Q3. The transistor Q2 and Q3 will be known as switching MOSFET. As they will be acting like switches, therefore we can represent the transistor Q2 and Q3 using resistors. During on state they will provide a very low resistance 1 kilo ohm. During off state they will provide a resistance of around 10 to the power 12 ohm. So I can represent the transistor Q1, Q2 and Q3 using a resistive network like this. See, here we are taking the output from the drain terminal of the transistor Q2, and the source terminal of the transistor Q2 is connected with the drain terminal of the transistor Q3 here. Now let me talk about the logical operations of NMOS NAND gate. At first I will consider the case when A will be at logic 0 and B will be at logic 0. A will be at logic 0. That means I will connect this terminal with ground terminal and this terminal with the ground terminal. 0 volt, 0 volt. In that case the transistor Q2 will be in off state. The transistor Q3 will also be in off state. When the transistor Q2 and Q3 will be in off state, their channel resistance R2 and R3 will be equal to 10 to the power 12 ohm. 10 to the power 12 ohm. See, this is a very high resistance. And when the transistor Q2 and Q3 will be in off state, their source and drain terminals will act like open switch. That means I will disconnect the source and drain terminals of transistor Q2 and Q3 from the circuit. Okay, see, if I disconnect the source and drain terminals of the transistor Q2 and Q3, I will get a circuit like this. That means I am disconnecting the 2 ends of the R2 and R3 from the network. Therefore, the drain current ID that should be flowing through this path will be equal to 0, because there is no close path from this source to this ground terminal. Therefore, ID will be equal to 0. As ID will be equal to 0, therefore the voltage drop ID R1 will also be equal to 0. That means our output voltage VO will be equal to plus VDD or equal to plus 5 volt, which will indicate logic 1. So for input A and B0, I will get output logic 1. Okay, now consider the last case when A will be equal to 1 and B will be equal to 1. That means I will apply plus 5 volt between this terminal to ground terminal and plus 5 volt between B terminal to ground terminal. B will be at logic 1 and A will also be at logic 1. In that case, both the transistors Q2 and Q3 will be in on state. When the transistors Q2 and Q3 will be in on state, their channel resistance will be around 1 kilo ohm. 1 kilo ohm. Now see, when the channel resistance will be 1 kilo ohm, look here, I will get current flow ID from this source towards this ground terminal. Okay, so ID will not be equal to 0. Now see, what will be our output voltage? See here, from this terminal to this terminal I have a resistance of 1 plus 1, total 2 kilo ohm. So if I want to calculate output voltage, I will apply voltage divider rule. That will be 2 kilo ohm divided by 100k plus 1k plus 1k into 5 volt. Therefore here I will get 2 divided by 102 into 5, and that will be around 0.098 volt, or I can approximate this to 0 volt. Therefore you will see for inputs 1 1 our output will be at logic 0. Now consider the case when A will be at logic 0. A will be at logic 0, that means I will apply 0 volt here. That means this A terminal will be connected to ground terminal, and B will be at logic 1. That means I will connect a 5 volt voltage source between this terminal to ground terminal. Therefore you will see, as A is at logic 0, it will be in off state. As it is in logic 1 or 5 volt, it will be in on state. Therefore you will see R2 will be 10 to the power 12 ohm of state resistance of transistor Q2, and the on state resistance of Q3 will be 1 kilo ohm. Now see, as the transistor Q2 is in off state, its source and drain terminals will act like open switch or open circuit. So I can disconnect the source and drain terminals of the transistor Q2 from this network. If I disconnect the source and drain terminals of the Q2, our circuit will look like this. That means I can disconnect the two ends of the resistor R2 from this given resistive network. Now see, as a result, ID will be equal to 0 because there will be no current flow. There will be no closed path for current flow from this terminal to this ground terminal. Okay, as ID will be equal to 0, here ID R1 will also be equal to 0 because ID equal to 0. So there is no voltage drop across this 100 kilo ohm resistor. Therefore our output voltage VO will be equal to plus VDD or plus 5 volt, or it will be at logic 1. Okay, now let me consider this case when A will be at logic 1 and B will be at logic 0. That means this terminal will be connected to ground terminal, and I will apply plus 5 volt between this terminal to ground terminal. So our transistor Q2 will be in on state. The transistor Q3 will be in off state. So the on state resistance of transistor Q2 will be 1 kilo ohm, but the off state resistance of transistor Q3 will be 10 to the power 12 ohm. Now see, as the transistor Q3 is in off state, its source and drain terminals will act like open switch or open circuit. So I can disconnect the two ends of the transistor Q3 from the network. That means I can disconnect the two terminals of the channel resistance R3 of the transistor Q3. Okay, therefore you will see there will be no closed path from this terminal to this terminal. ID will be equal to 0. As ID will be equal to 0, therefore ID R1 will also be equal to 0. Therefore our output voltage VO will be equal to plus VDD, or plus 5 volt, or our output will be at logic 1. See, this is the truth table of a NAND gate. As I can verify the truth table of a NAND gate using this logic circuit, I can say that this is a NMOS NAND gate. That's it. Thank you.